Sí, ya lo conecté. Ahorita empieza.
Sorry.
We are ready. We are going to start the next talk.
Afternoon, everyone. We're going to continue with the last track of the conference, track number 4. We're going to start with another keynote talk given by Professor Andreas Koster. You know very well by now. He's here from the SIMBA staff, and he's going to talk about the simple magnetic superatoms. And I think I'm going to change my career now, because if what he's doing is simple, I like to do that.
Thanks, Eduardo. Now, first of all, good afternoon all together. It's a real pleasure to be here, to have you here. And I would like to thank the organizers for giving me the possibility to be here and to talk to you about that. As you see from my title, this is not health information, obviously. So this is something that goes in the direction of cluster science and material science. And I thought when I prepared the talk, I would like to introduce you to this concept of superatoms. And this will be more kind of a review of works that people have done. I think over the last 40, maybe even 50 years, something will be really coming to the game are the magnetic superatoms. And this is where the concept of simple comes here in. Simple means here structural and composition simple, and not that the description by itself is simple. And then we will hear about this guy, thorium-55 plus. This guy has made really a story. There are 2 natures, and I think a science paper on this one cluster. We will hopefully understand why this cluster has made such a story in the scientific literature. And the last point here, this was my COVID activity. So when COVID hit us, our computer became empty because the students were at home starting to become depressive. So I had computer time. So I thought I do this and search for such magnetic atoms. Okay. Yeah, you know this already. I'm working with a program called D12K. This is a density function theory program. We had this in the course. And I have here a picture of one of our annual meetings. And here I really have to say thank you to this community, because a lot of the tools and a lot of the possibilities that I'm now using were not developed by me or even by my group, but they were developed by other groups, and they are inside this program. And it is really nice to have such a beautiful collaboration. And of course, I would like to thank many agencies here on the slide which have supported our research over the years. Yeah, let me start with something that is a peculiarity. This is a paper from '85, and it goes about polarizability of sodium clusters. So what is interesting on polarizability of sodium cluster? So polarizability is a microscopic quantity of electric susceptibility, which we already have heard about. So this is linear optics. If you want to go nonlinear, then you have hyperpolarizabilities and second hyperpolarizabilities. And what you see here on this slide is a behavior of this polarizability with cluster size. And these are clusters in the NOVA, ultra-high vacuum flow tube experiments. And what you see here is the bulk limit. And what you see here is the atomic limit. And now you can ask the very simple question, what happens to a property of a system like this polarizability if I make my system smaller and smaller and smaller and smaller? And what you would expect is that you somehow see here some kind of smooth curve, maybe that from the atomic polarizability goes to the bulk limit. But this is not what you see. You see here a regime of measurements of the sodium polarizabilities where it looks quite erratic. And this was a discovery that was at that time quite new and has made research for at least 20 years afterwards. And today, it is rather clear that the transition from a macroscopic object, from a microscopic system into the atom is not continuous. That there is something in between which is very different. And this difference, of course, depends on the type of system you're looking at. And here we look at relatively simple metal clusters. If you look at this in more detail now on the cluster size, you have here the atom, and here you have nine atoms in this cluster. You see kind of oscillations at the dimer. You have a minimum in the polarizability, and also at the octamer, you have a minimum in this polarizability. And at the other part here in between, you can think about that there is a relative smooth transition between these two minima with the maximum at the triangle. So why do you see such minima in such kind of quantity? Well, you have other experiments. And the experiments that are most, let's say, common to cluster science, which, as you can already now imagine, is at the lower scale of nanoscience, are such type of mass spectra, where you can see kind of peaks that are particularly high. And they have been interpreted since the first recording of such spectra as systems that might be particularly stable, thermodynamically stable. Yeah, that is something that you can read out of this. And you see here that they are very characteristic numbers, 9, 21, 41. Remember, these are cations. These are cations. So if you think about the number of electrons, and this is 8, this is 20, this is 40, this is 50. And another experimental evidence on kind of not continuous behavior you can see on this slide here, which is the ionization potential of these clusters, again, as the size of these clusters. And you see the strong oscillation. Yeah, so where you have very high ionization potentials at some points and very low ionization potentials. And these are sodium clusters. So this is very, very simple material. And what people really extracted from this experimental evidence was a model. And this model was motivated by what we know from atoms. Yeah? So if you think about the atomic electronic distribution, you are very much aware that you have shells. Yeah? So you look at the periodic table and the ordering of the elements in the periodic table reflects the shells of the system. Yeah, so you have S shells, you have P shells, you have D shells. And when you fill these shells, so when you have something like an S2 configuration, or you have an S2 P6 configuration, or so on, then you are coming to raw gas elements. So to elements that are not very reactive, that are in their form stable. They don't want to do chemistry. And in this form, the mass spectra, these peaks in the mass spectra, have been very early interpreted in such shell structures. So if you take, for example, a cluster with 8 sodium atoms, something like with 9, so here's the Na9 plus, then you have in this cluster 8 electrons. And the idea is that each sodium atom gives an electron to a finite electron gas that is around this cluster. This is, of course, a cartoon. This is not reality in the sense that you really can measure this, at least not until now. And if you then look at this part here, which are solutions of the electron gas in a sphere, then you see, I have again shells. And I now have shell closing. So my lowest shell is 1s. If I put 2 electrons inside, I have 1s2. So I have a particular stable closed system. The next shell is the 1p. The main quantum number here changes because this is without a radial potential. Yeah? And then you have 6 electrons in the p shell. Together with the 2 electrons in the s shell, you have 8 electrons. And this again is a stable system. And so people have said, oh, this peak here at Na9 plus, this peak is there because it's an 8 electron system. And this peak here is a 21, it's a 20 electron system. This peak is here because I have S2, P6, D10, S2. And so in this form, people have very early, in the middle 80s, without any really calculations, started to do such shell models. And they have used this for sodium, they have used this for potassium, they have used this also for other systems, aluminium, for example, later on. And they have found these shells. And then there were, of course, all kinds of modifications of the sphere. You can make it ellipsoidal and you can distort it. And you can then basically explain everything you want. This is typical for a model, of course, then at a point. Now, the situation became really interesting when it was possible to do density functional theory calculations on these systems. Because when you did DFT calculations on the system, you could see these orbitals. And that is somehow strange that you can see these orbitals, because this is a model, this is and in fact no quantum mechanics inside, but you can see these orbitals in quantum mechanical calculations. And you cannot measure orbitals, but you can interpret these orbitals in form of certain kinds of ionization and electron affinities in terms of propagator theory. And then these orbitals do gain a physical reality in form of ionization or in form of an electron affinity. Yeah, and so I was very happy to hear a couple of, I think a day or 2 days ago, that adsorption is not isotropic. The future will show that also ionization is not isotropic. There are now experiments which are radial resolved photoelectron spectroscopy, and they show when you ionize the system, the electron does not go in all directions with the same probability. It goes in certain directory with preferred probability. These things here do define these directions. These are the poles in propagator theory that you can identify to with these orbitals in Kohn-Sham density functions here. For us here, because we want to go magnetic, there is one thing in this analogy which is really different if you go from an atom to such a cluster, which we call then a super. The difference is, if you look at an atom, the nucleus of an atom is, for us, in our abstraction, a point in space. So there is no spatial distortion for the nucleus in an atom. It's impossible. A result of that, and the pure quantum mechanical result of that, are the Hund's rules. So if I ask you what's the ground state of the carbon atom, then it's relatively easy. You only have to count the valence electrons. So I have 4 valence electrons. 2 of them I put in the s orbital. That gives me an s2 here, valence. And 2 other electrons I put into the 2p orbitals. The 2p orbitals are triple degenerated. And now the question is, how do I put the electrons into these 2p orbitals? I can put them with spin up, or I can put them with spin up, spin down. And Hund's rule says you put the electrons first with the spin up. So you fill the degenerated orbitals only with electrons of the same spin. And only if you have done this, then you fill with the opposite spin. That is Hund's rule. As a result, if you fill 2 electrons into the 2p, you have 2 electrons with alpha spin. And that is a triple. So this is a high spin system. You don't see high spin systems very often in molecules. Why not? Yeah, because molecules, they can distort their molecular structure. We call this a Jantella distortion. And by the distortion of the molecular structure, the degeneracy of the orbitals is lifted, and the electrons can fall down and can pair in one of these orbitals and gain energy. That is a Jantella effect. And that is very, very common in molecules, particularly if you know about coordination chemistry. You have all around, you have these Jantella effects. These Jantella effects you also have in these clusters. So as a result, you always find situations like this. You do not find the degeneracy of these orbitals. Yeah, so if you have, for example, a cluster with 4 atoms, if you make it in a square arrangement, these 2 orbitals will be degenerated, they will be at the same level. Immediately, the cluster will do Jantella distortion, the orbitals will go away from each other, and you will occupy one, and by these diminishing of the energy, you stabilize the system. That is what you always see. And this now explains you very nicely why you have these oscillation in the ionization potential. If you have an even number of electrons, you have a situation like here. If you have an odd number of electrons, you have 1 unpaired electron. And this 1 unpaired electron can be ionized easier as out of it. Yeah. Could you give me a sign by 5 minutes? Sure. Because, okay. So this is the idea. And now, with this idea, with the calculation, so what are superatoms and how do they are realized? So the first thing what we already have discussed was shell closing. These peaks, which you see here, they are corresponding to characteristic numbers of electrons, not atoms, electrons in the system. Yeah, to characteristic number of electrons in the system, they are thermodynamically particular stable. But it's not only the stability, the thermodynamic stability, but it's also the properties. If you now look again on these minima in the polarizabilities, you see these minima correspond to systems that have also these kind of closed shells. And now you understand what happens. If these shells are closed, then the electrons are more frozen together. If now an electric field comes, then the distortion is smaller, so the polarizability of the system is smaller. So you have a very rational and simple idea what is going on there. Now you can say, okay, this looks all very nice, but I don't have ultra high vacuum apparatus around the corner. I don't have a flow tube. And so does this have anything to do with real life? Well, that is brutal chemistry. If you think about mercury, then mercury stands under zinc. So for physicists, I think you all know zinc oxide, that's ZNO. So there is you have the zinc cation, and it is a double charged positive cation. Yeah, and mercury stands below there, and it should be also double charged positive cation, so it should be Hg2 plus. But if you put this poor Hg2 plus into a solution where you also have elementary mercury inside, then something very strange happens. This is called a disproportion reaction, and it builds an ion which is Hg2 plus. And if you count the electrons and if you do the quantum mechanical calculation, you see that this is a superatom. Yeah, this is an S2 system which you have there. But you can do much more. Yeah. This is a beautiful work from the late Will Castleman from Penn State. So what do they do? They produced in the gas phase size-selected arsenic clusters, RS7. And these RS7, they were RS7. This is just, when you go into the super atom concept, this is just one electron before you have shell closed. Yeah? If RS7 would have an electron more, it would be a shell closed. And then they deposited this by soft landing on a substrate. And they observed this kind of solid, where you have a potassium atom, which becomes a potassium plus, and an RS7, which becomes an RS7 minus. So the RS7 now takes over the place, for example, of a chloride or of a fluoride atom in such kind of assemblies. And today there are thousands of these assemblies produced exactly after this concept. And it is even more interesting. There is a theory in solid state chemistry which is called simple phases. And it turns out that simple phases are nothing else as condensed superatoms. Yeah. So we came from flow tube experiments in the ultra high vacuum to simple phases that are known since 1934. Last but not least, this is a famous Stanford experiment. This is gold 102 ligand stabilized. This is the first superatom in solution. A ligand stabilized atom, superatom in solution. You can produce this size selectively in the kilogram amount. Yeah, that's a lot of stuff. What you can do with this if you have enough money for the gold, of course. And so this is something there have been now many kinds of papers and also whole journal titles about the periodic table goes three-dimensional. So that with these superatoms you have a new dimension in the periodic table where you can use them as cations or as anions in such kind of system as you see there in the potassium arsenate system I showed you. Now, here's now a point where one has to be a little bit careful, and I put this in. Also, not all clusters and not all protected clusters are superatoms. And superatoms really are shell closings. And for example, we a couple of years ago found a palladium-13 ground state structure, which was very unusual. So 13 atoms, metal, you would guess it's an icosahedral. But palladium-13 ground state is not icosahedral. Has this double layer structure down here. This is also experimentally verified in the last years. And we thought, oh yeah, this is a superatom probably because of the strange structure, because strange structures have something to do with superatoms in the sense. But if you then look into these orbitals, this is not really true. This is a structure that is somewhere in between. Yeah, it has some superatom behavior, You see this down here. But it also does have behavior that are typical normally covalent bonded systems. Another very recent example from us is this copper cluster here. This is a copper 20H11. And of course, when you look with the superatom googles on this, you say, oh, this is a copper 20 cluster, which has hydrogen somehow absorbed to each other. This is a hydrogen source, right? But it is not. Actually, if you put the hydrogen out, this cluster goes, dissociates or goes, so breaks up. And the reason for that is, if you cannot really see this, but if you look at these things, these are the coppers, and here in this picture, it looks so as if these coppers are bonded to each other. But in reality, if you do an analysis, you see that the coppers are not bonded to each other. They are bonded over the hydrogens. And that is the reason why the cluster then, when you take the hydrogen out, breaks in parts and it's not recoverable. So it's not a recoverable hydrogen source, but it is a hydrogen source anyway. Okay, now I gave you a very brief introduction into superatoms, into the history and also into the literature of superatoms. And now we come more to the work which we have done in this field, and these are magnetic superatoms. And the first work we did was on such kind of silver vanadium clusters, where you have also a couple of silver atoms and you put a vanadium atom inside. And now you know vanadium has S2D3 configuration, and these D3 electrons, because Hund's rule apply, they are unpaired. And so they make the system, the vanadium atom, magnetic in this sense, if it would stay in this thing with 3 unpaired electrons, for example, in the D shape. And what you can see is that you also see here these kind of peaks inside the mass spectrum, and we already know, okay, these are particularly stable systems. And what you then see is that the vanadium oxidation state in these clusters changes. So the vanadium, for example, in this cluster is not the same as the vanadium in this cluster. Even so, from the structure, it looks, oh, this is the same. But it is not. Look at this here. This is the multiplicity down here. This is a high spin cluster, the ground state. This is magnetic. If you go down to the silver 14, this is a low spin cluster. This is not magnetic. So the vanadium changes its nature in these clusters. And you can now, with a counting of electrons, obtain more or less the idea which of these clusters would be magnetic and which would not be magnetic. And so it's today a very accepted concept that you can make these kind of coin metal clusters magnetic by doping with transition metals. Yeah, that is something that is there. But of course, you have to be very careful with this, because you see, this here is the multiplicity. Basically, it's a measurement of the magnetism. And if you go to small clusters, this is magnetic, but then you get a quenching of these magneticity in these structures. And this quenching is for all of the coin metals, copper, silver, gold. It is a little bit different because the structures of the clusters change, particularly when you come to gold. I don't want to explain this here. This is really not easy, not simple. So I only want to show you on such an example what happens to the electrons in such a cluster. So if you think about that, you have these S shells, you have the P shells, you have the D shells in clusters. Yeah? If you go symmetry adapted until D, then the only point groups that can make these kind of 5-fold degeneracy are icosahedral point groups. Yeah? But these icosahedral point groups would end up in such a situation. And this situation looks already like this is the antenna distortion. Yeah? And in fact, it is the antenna distortion. You go here from the icosahedral symmetry into a tetrahedral symmetry. And you see what happens is it's a 5-fold degeneracy here, splits up. And you see here something which is quite interesting now, which goes one step beyond the electron counting with the super electrons, because now this cluster has stability because it is closed until here in a shell sense with alpha and beta electrons, and here it is closed for the alpha electrons. So if you count electrons, you should actually distinguish. You can count alpha electrons and you can count beta electrons. And it is not necessarily true that shell closing is always together with alpha and beta electrons. You can have shell closing in alpha electrons and shell closing in beta electrons. It is different. That is exactly what you have here. With shell closing in beta electrons, it's a TG state, and you have shell closing at the alpha electrons in the EG state. Now, this is a stable cluster in the sense of that it has a peak in the mass spectrum. And if you look there, this is a distortion to tetrahedral symmetry. This is a silver cluster, the analog. This is the first one was a copper cluster, copper 12. This is silver 12, and it goes into the octahedral symmetry. And again, you have the same kind of splitting, but you go into another point group family. And that is because the D manifold lies in different positions inside these orbital diagrams. Yeah. So now I switch gears and I come to sodium 55 plus. So what makes sodium 55 plus so particular? Well, the first thing is I must honor the guys to whom honor belongs. These are the experiments. This is the Haberland group from Freiburg, and they were the first who measured a heat capacity in one molecular system. This is heat capacity of one cluster. This is the melting of a cluster, of a finite system. And you see the heat capacity looks quite different. It looks actually, if you look from a thermodynamic point of view, as if this is a second order phase transition, but it is not, because it's a finite system. Yeah? Normally, heat capacity, transition, space transitions go in such a form. Here you have a continuous form because you have a finite system. And the melting temperature is at the maximum of this heat capacity curve here around the temperature. The experiment is fantastic. And it takes an own talk to explain all these experiments. It's really a fantastic experiment. So people were able to measure heat capacities in individual molecules, in individual clusters. And then I saw this was around 2000. I saw this picture. I said, I know exactly what is my dream. I want to calculate this heat capacity curve. That I would really like to do. I would like to calculate this heat capacity curve. Because what you see here is basically the same as binding energies. If you think about how do you say that your electronic structure method is good? Well, you have the G2 set or the G3 set where you compare binding energies of certain systems with experimental measurements. Here, you have an experimental, accessible, direct measurement of the dynamic of the system. So this is the dynamic equivalent of binding energy. I said, this would tell me, at that time, for example, there was Kappa-Inegro molecular dynamics, there was Born-Oppenheimer molecular dynamics. Which of these dynamics were better? Okay? This is a point where you can clearly say, this molecular dynamics gives me the correct experimental melting temperature of this finite system, if you can use this ab initio, of course. So what is particular on sodium 55 plus? Right? If you want, this is a melting temperature in a kind of normalized way, and this here is an inverse cluster size. Here are clusters that have 1,000 or 10,000 of atoms. And if you look at the melting temperature of sodium 55 plus, it has a melting temperature that is the same as the melting temperature of a cluster with a few thousand to 10,000 atoms. So Y to the heck has a system with only 55 atoms, a melting temperature of an almost, from my perspective, almost macroscopic size, right? 1,000 atoms is big. Yeah. So why is this so? And this has bothered the experimentalists so much that at least 3 completely independent measurements with very, very different methods on this one cluster have been done. And look at this, the melting temperature is within a range of 10-20 Kelvin, always the same. This is perfect. So from the experimental point, this is absolutely reproducible. This looks in a graphical way. If you put this in, this here is sodium 55 plus. This iodide, sodium 55 plus. If you change only one atom, you have already a difference of 20 Kelvin in the melting temperature by one atom change. Oh shit. That's huge. Okay, so we did the simulation. And this here is our melting curve. This is our melting curve. And this is experimentally almost perfect. And now I show you something. This is a sodium 55 plus in the singlet state. This is what you would expect. This is 54 electrons. And if you follow my kind of idea of the Antella effect, this is what you would expect. This is the sodium 55 plus in the quintet state. And they don't know an experiment in which kind of multiplicities they have the cluster. They have no idea about that. And this is a molecular dynamics simulation here, first principle. And this is really the beginning of this trajectory. And if you look at the 2 clusters at the beginning, they look really very much the same. They look almost icosahedral. And only after a few hundred femtoseconds, really a few hundred femtoseconds, the singlet state distorts in something ellipsoid. And it never comes back to the icosahedral structure. And the quintet state always stays inside the icosahedral structure. All the way of this kind of trajectory stays inside the icosahedral structure. So the quintet state melts as an icosahedral. There's no other cluster that melts as an icosahedral in this series. Because if you put an electron out, so this is a singlet, and this is a quintet. This is a Wundt type cluster, and this is highly magnetic. Yeah, this is magnetic sodium. This is the photoelectron spectra, and we have calculated the photoelectron spectra, and we were able to quantitatively reproduce the experimental photoelectron spectra. This peak here, this small shoulder, is the smoking gun that sodium 55 plus is in a quintet state. And here we have a situation. This is the splitting of the 1G level in sodium 55 plus. And as I told you, in cluster size, in this size range, an atom counts. If you put an atom to it, or you put an atom away from the cluster, you get different physical properties of the system. In this particular system, not only an atom counts, an electron counts. This is sodium 55, and you see here a Antella distortion. Yeah. So there's you take one electron out of the system and you get a Antella distorted system. This is really sodium 55 plus. That is a system where you have the right electron number, the right atomic number to have these icosahedral melting. Okay, 5 minutes. The boss said, so I have to do. Okay, so you see, this is what I wanted to show you in more detail, but time moves out. I was searching now for new magnetic superatoms. So, of course, after we published sodium 55 plus, the alkali metals were within 6 months scanned. I mean, their publications, they have all shown the same thing. So this column is gone for me. And then I said, no, but listen, what is What is with this column? What is with the coin method? Even for practical reasons, because who wants to make experiments on sodium? Nobody really. Sodium is not so nice, and don't want to burn down your laboratory. But copper, silver, gold, that is something you can have. I mean, the guys in Stanford, they had gold cluster. So can we not do something like this? There's a long story actually on the theoretical methodology. This is not a trivial calculation. These are calculations, I would say, only with V1 you can do these kind of calculations. There are no other program that can do this calculations. So to make a long story short, what did we found? We found that indeed sodium 55 plus has a quintet ground state. Copper 55 plus has a quintet ground state. So this is a coin metal cluster that is likely to be very magnetic. So we don't have the photoelectron spectra. That is the next thing. We will calculate now the photoelectron spectra of this guy, also not a trivial case, in order to give it to experimentalists so that they can measure copper 55 plus. Interestingly, neither silver nor gold have quintet ground states. You cannot make them magnetic. Neither silver nor gold. You can make copper magnetic, you can make sodium magnetic. So it seems that Hund's type clusters are only living in the upper part of the periodic table. When you go down in the periodic table, they disappear and the antenna distortions become dominant. And there's a reason for that, which is the relativistic contraction of the bond. Well, this is what we do because only a technical issue. We have to go to this guy here to do the calculation, and we need to do there in molecular dynamics that is excessively parallel. For this, we have implemented parallel tempering, BOMD. This is a molecular dynamics that calculates simultaneously different temperature ranges. And so you can parallelize this excessively. We have run BOMD calculations up to 6,000 cores. So this is something for exascale architecture. And this is my conclusions because of the 5 minutes. You can read this here. So there's a point. Why is sodium 55 plus not seen in the mass spec? I mean, if I say sodium 55 plus is a magnetic superatom, and then it should be thermodynamic. Yeah, it is. It is thermodynamic stable as long as it is a node. It's a radical. And what are radicals? They react immediately. So the point is that if you have sodium 55 plus in your cluster beam, and 2 sodium 55 plus are coming together, well, they react to each other. That is the reason why you don't see them. Yeah? So we do not have the full electron spectrum for copper 55 plus, we're working hard on that. And we have finally a very simple thermodynamic explanation why the melting temperature of sodium 55 plus is so outstanding. Yeah, that is because the melting entropy, it's an icosahedral melter. So the melting entropy is rather small. Yeah, and when you have a small melting entropy, then the melting temperature, if the melting heat is more or less the same, goes up. And that is the reason why you see this peak in the melting of sodium 55 plus. Okay, next challenge, lipid stabilized magnetic superatoms. That is for the next decade. Okay, thank you so much for your attention.
Thank you, Professor, for the beautiful talk. Questions?
That is the first one.
Thank you so much for the nice talk. I have a couple of questions. First one is that so you choose like sodium 55 plus and also copper 55. So what happens when you reduce the atoms to single atoms?
If I reduce the atoms further,
what is the main difference when you reduce to single atoms? Now people are doing gold, silver, everything and up to single atoms.
yeah, if you can, there's not a problem, but the point is, also, if you're interested in the magnetism, yeah, so if you want to have an intrinsically non-magnetic element like sodium. So if a student tells you sodium is magnetic, what do you do? Thank you very much. Right? So what I'm telling you here is that if you go to a very specific cluster size, this intrinsically non-magnetic element produces magnets. And this depends on the number of atoms, because this means the structure. It must be icosahedral. And it depends on the number of electrons. That is what you see here. Now, this is the diagram for sodium 55 plus. And these are the electrons that make it magnetic. Yeah? If you put one electron more inside, so you go to the sodium 55, you see a pairing here, and you see that this is no longer degenerated. Yeah? This means the cluster distorts out of the icosahedral. Yeah? It still has a certain amount of magnetism, but it is less. Particularly, the melting goes down, because this is now no longer icosahedral melting, because the icosahedral symmetry is. Yeah.
I have one more question. In the experimental results, how many atoms they measure in the clusters?
They can go down below sodium 55 plus. There. You see, this here is 54 plus.
Okay.
I think they are down up to something like sodium 30.
Okay.
And then at a point it becomes really complicated, because the height of the heat capacity curve, of course, also depends on the number of atoms you have in the system. And then at a point it is no longer resolved.
Okay. Thank you.
Presentation. I would like to ask, how do you propose a form for your cluster? The form, the geometry.
There's a form comes out of such a simulation. So we run Born-Oppenheimer molecular dynamics simulations at certain temperatures. This is at 250 K. And then we take snapshots out of this trajectory and we do local optimizations. And then we look if these optimizes to different structures so that we have different isomers, or if this all optimized to the same structure. So in this particular case of sodium 55 plus, the icosahedral structure has an enormous large catchment region. And so if you look at here, or here, or here, and then you do a local optimization, you always optimize to the icosahedral structure. So of course, if the structure has much less symmetry, then you get to different structures, and you have to run these molecular dynamic trajectories for a rather long time. And so we are talking about 100 picoseconds or even nanoseconds.
Is it equal, or is it rather similar for sodium and copper clusters?
We haven't done this for copper. For copper clusters, I have assumed the icosahedral structure from the sodium, basically scaled the bond lengths and then locally optimized. But I have not done the real search for the copper. In this respect, this is what we do here. This is if you do this, if you do parallel tempering D on D, what you do is you not only run the cluster at one temperature, but you run the cluster at different temperatures. Yeah. So many temperatures. So the cluster is running, and after some steps, let's say 100 steps, you now look how close are energies of different trajectories. And if they are close enough, you interchange the clusters. That means that here at the lower temperature, you over time collect the most stable cluster. And this is, if you have enough trajectories, enough temperatures, and enough long time for the propagation, this is a global optimization without any bias. Of course, we cannot run this for, let's say, 10 or 100 nanoseconds. We can run this maybe for 100 picoseconds. But this is exactly your question we want to do for copper. We feed it in here, acid equals anhydride. We have different temperatures, let's say from 300 K to something like 1000 K. And then we let this run for hopefully as long as we compute Canada and losses. That's a limiting factor.
Okay, last question. And how much time do you expect it to last?
Also, the sodium 55 plus calculations were done on the old West grid, and they were run on 128 cores each trajectory, and we have altogether sampled for 5 nanoseconds, and all the sampling together took half a year.
Thank you very much.
However, will not be faster.
For questions, thank you very much, Professor. Again, thank you. We will see you next year in India. Next talk is an invited talk given by Professor Jorge Castro Ramos from the Instituto Nacional de Astrofísica y Óptica y Electrónica en Hawaii, México. El doctor Castro recibió su PhD in Optics from the National Institute of Optical Astrophysics and Electronics. He's one of the creators of and leader of the biomedical instrumentation. More than 50 international publications. His research focused in optical design, systems, quality verification of visions, and in the area of the biomedical optics, he applied Raman spectroscopy to develop a painless detection technique of diabetes and chronic degenerative diseases through biomarkers. Welcome, Professor Jorge.
Thank you for the presentation. I give my apologies, but I was confused and I don't know if I speak in Spanish or in English, and I prefer to speak in Spanish. I'm sorry, but I don't prepare my. Tengo que comentarles, ¿verdad? Que pues agradezco, ¿verdad? La invitación de los organizadores. Y bueno, de lo que voy a platicar es un poco de las aplicaciones de la
I am going to talk about the spectroscopy on Raman to detect the degenerative chronic disease. This is part of that we know about biomedical optic. Actually, to realize the detection cancer tumor, we only have to realize some surgery and extract part of this tumor and realize a biopsy and decide if it is benign or malignant. In our group, we use light to detect if this tumor is benign or malignant. We illuminate the biological tissue, the radiation that we use penetrates in the basal layers. There are many other applications about biomedical applications. As an example, with the dentist, they use mechanical procedures to remove bacterial layers. But also, nowadays, light is used to remove these bacterial layers.
de grasa, bueno, después
in the skin. Also, we use light
bueno, pues estos son los
to
antecedentes,
treat
¿verdad?
the skin.
De lo que es la óptica biomédica y pues yo quiero platicarles, ¿verdad? De lo que hemos estado
These
haciendo
are
clínicamente, ¿verdad? Ya les platicaré de la parte experimental y ahora de la parte clínica que hemos estado desarrollando en algunas instituciones.
I'm going to talk about the clinic.
¿Para qué? Pues para determinar entre cuando un paciente está sano, cuando no
The
está
clinic.
sano, cuando tiene un tumor maligno, cuando tiene un tumor benigno. Y bueno, pues esto lo hacemos mediante la
Experiments
¿verdad?
done in our work,
mediante el análisis de componentes
basically in the principal component analysis and neural networks analysis. We make this idea comes from
tienen miedo incluso a una inyección, ¿sí?
come from the necessity of the people
Esto
in front surgery need.
Bueno, pues hay toda una rama, ¿verdad? Conocida como la atomofobia. Esto pues obviamente causa mucho estrés, mucha tensión, ¿sí?
This
Y bueno, pues esa
causes
fue nuestra
stress
idea de contribuir
in people.
con esto. Y nos dedicamos, bueno, pues al estudio de las enfermedades
We study
crónicas.
chronic
Estas son
degenerative
enfermedades, ¿verdad? Que
disease
se presentan en el humano durante un tiempo pues bastante
presented in human
grande.
for a long
Son
time.
enfermedades que, bueno, pues uno las puede tener
These are
todo el tiempo y no
diseases
pasa nada, pero en algunos casos, bueno, pues estas
that
llegan a
sometimes we have for a long period of time, but
¿Cuáles son
sometimes
estas enfermedades? Bueno, pues aquí en México,
they are very hard to deal with.
Obesidad, sobrepeso, cáncer, ¿verdad? Enfermedades cardiovasculares. ¿Cómo es que nosotros estamos proponiendo nuevas técnicas, ¿verdad?
What's our proposal to detect some
Bueno, voy
of
a
this
empezar
disease?
con la diabetes, ¿sí?
We will start with diabetes.
Sabemos, ¿verdad? Es una
As we know, is a chronic and degenerative disease
muy diversas causas,
that
¿verdad? Una de
occurs
ellas,
for many causes.
obesidad, por la mala alimentación, los antecedentes familiares, la edad avanzada, ahora
Age,
la
bad
pandemia, la falta de actividad.
habits in food, and lack
Los
of
métodos
physical
tradicionales
activities
para determinar si una persona tiene diabetes
are the
o
main
tiene
causes
diabetes, bueno, pues es mediante
for
la
diabetes.
extracción de
The
sangre,
main
¿verdad? Sea esta
way
intravenosa
in
o
which
sea
we
esta
detect
mediante
diabetes is
una
because
lanceta
is
en la yema de los dedos, pero siempre es
with the
extracción de
detection
sangre.
in
Esto,
blood
bueno, pues es
samples.
doloroso y es traumático.
This
en
is
muchas de
very
las
traumatic in patients.
ocasiones, ¿verdad? Bueno, pues por eso es que nosotros estamos proponiendo
So
un
we are
método
proposing
no
a
invasivo,
new
en que no
method,
necesitamos extraer sangre, necesitamos solamente
less invasive
eliminar
for the
la piel,
patient.
tejido biológico.
We only need to
Usamos,
use
agentes
light
químicos, que también es algo que se
to
necesita
detect
en los laboratorios. Es un
diabetes.
método, rápido, ¿verdad? No
It's
hay
a
riesgo
fast
de infección, pues
method,
usamos, jeringas,
and we don't
lo que
use
usamos es la
syringe,
espectroscopía.
and we use spectroscopy to
En la
detect this.
espectroscopía, bueno, pues es el estudio de la interacción entre la materia.
Spectroscopy is the study between
Esto, pues,
matter
antecedentes con Newton en 1704, ¿verdad? Que hace incidir luz,
and
¿verdad?
electromagnetic waves.
Pues, esto que llamó como el espectrum, ¿verdad? El espectrum, pues es lo que conocemos ahora. Nosotros, en nuestro caso, ¿qué usamos como materia? Pues usamos el tejido biológico, ¿verdad?
We use
Usamos
biological
usamos
tissue,
orina, usamos
blood,
de cervix, usamos para la artritis, usamos los huesos.
bones,
Para la diabetes, bueno, pues
and
utilizamos
blood
la piel.
to detect
Para un cáncer, bueno, pues utilizamos los tumores.
diabetes.
Eso es lo que
And to
ponemos
detect cancer,
frente,
we use
la luz, ¿sí? Hacemos pasar por el elemento dispersor y bueno,
cancer cells.
pues nos interesa determinar cómo es el espectro de cada uno de estos. Lo que nos ha dado
Our
los
interest
mayores
is the
resultados,
spectrum of these
los que quiero
samples.
hablar, es de la espectroscopía Raman.
I am going to talk about Raman spectroscopy. In 1928 and 1930, Professor Raman discovered the Raman spectroscopy.
Como un puño de azúcar, ¿verdad? Que es lo que hemos estado tratando. Y bueno, pues esto tiene pues, una gran cantidad de trozos, ¿verdad?
He used sugar,
Atómicamente, bueno, pues ya
and we can see the atomic structure of sugar
átomos que el modelo clásico
and light to detect this structure. We use the atomic structure of these atoms, and we use light to detect the vibration of these atoms. We consider these atoms joined together with a constant, like a spring. Classically, in classic physics, when we induce light over matter, we have 2 or 3 different lengths, and we obtain Rayleigh light, and anti-Stokes disbursement spread and anti-Stokes.
Los modos fundamentales de vibración cuando uno hace incidir luz sobre el tejido biológico, bueno, pues aquí están, ¿verdad? Este es un ejemplo de una molécula de...
When we excite matter with light, we have several behavior of the atoms and the basic modes of vibration in matter. If this happens in water, when we excite water, in bigger molecules we have and more ways of vibration. We use a very high number of biomarkers that indicates biological states of the patient, and that indicates the health status of the patient. Las bandas de remisión y bueno, las frecuencias de oscilación a las que nosotros tenemos. Esto es lo que analizamos primero, ¿verdad? Analizamos glucosa, sabemos que pues this is one of the first things we analyze in patients, sugar present in blood, molecules of glucose, and the basic numbers for a healthy person are around 108 milligrams per milliliter and higher in patients with sugar in blood. We analyze these concentrations in blood to resolve this equation. Sometimes it's hard to obtain some of these biomarkers in blood. El porcentaje, bueno, pues también es conocido para clasificar cuando una persona es diabética o no es diabética, y bueno, pues lo que nos interesaba de esta mezcla pues es controlar la cantidad de solvente. Este es el arreglo. This is the experimental setup. Several biomarkers, syringe of precision, and water. We need to avoid cross-contamination with bacteria from the medium. This is what we found in our characterizations. For several concentrations, we obtain several spectroscopic detections in persons with diabetes and without diabetes. We observe several differences between this spectroscopy data, how to obtain computational data from these measurements, how to classify this spectrum. We use principal component analysis in this spectroscopic data, as well as we do with our students. We have several measurements. We obtain the mean and the covariance, and we associate these results with the subjects from each. And then we can group these results with the capabilities of a person. So if the student is good in Spanish or mathematics, you can separate depending on the characteristics.
La parte cualitativa no es suficiente, necesitamos conocer una parte cuantitativa.
We need quantitative and qualitative analysis to complement principal component analysis. Another way is to use support vector machines in a way to geometrically find the division of different classes. For example, we have here all the students associated with social science and the students associated with mathematics and physics, for example. In principal component analysis, we need to find a plane to separate these classes.
Los puntos márgenes, bueno, pues son los que se conocen como los vectores de soporte.
These are vector support points, and the technique is related to find this surface known as kernel. This other distribution has similar characteristics. How do we obtain a shape to separate these classes? We need to add another extra dimension to separate these characteristics and elements. So we try to find this surface to separate these groups. There are many surfaces and vectors. We have polynomial and perceptrons to classify. With all these tools, we went to health centers to find patients and measure the skin of them. So we measure several places from the skin, and we obtain the spectroscopy of these measurements, and we apply the principal component analysis to differentiate patients, health and unhealth patients. Also, we use urine of these patients. A person with diabetes has differences in these urine samples. In urine, albumina is present or not in these samples. So we analyze urine to detect albumina. We use support vector machines to analyze this spectra from these patients. We deal with several diseases.
la para igual detectar
and we use several
cardiovasculares.
chemical components to detect these diseases.
Pero ahora lo que cambió fue el marcador. Este marcador, bueno, pues también tiene su propio espectro, ¿verdad?
We are looking for several components in the samples to detect this disease in several patients, like cardiovascular disease. Again, we apply principal component analysis to separate health and unhealth patients.
También estuvimos analizando, bueno, pues es la saliva, ¿verdad?
Another element that we use to detect this disease is saliva from patients.
Analizamos la saliva mediante el método de babeo pasivo, encontramos el espectrograma de la saliva y
Also, we analyze the spectra of samples of saliva.
entre ellos, y bueno, pues como todo, ¿no? Después de estas novedades químicas, ¿verdad? Pues se nos ha estado haciendo una buena propaganda, ¿verdad? Ahora, bueno, pues continuaremos con nuestros análisis clínicos para que sean implementados en los hospitales y bueno, pues para determinar si una persona es diabética o no, si presenta hipertensión o no.
The use of light in
Y bueno, pues eso es lo que hemos estado haciendo.
samples obtained from patients
Para diagnosticar enfermedades crónico-degenerativas.
is a method to detect chronic and degenerative disease non-invasive in a non-invasive way.
Jorge, for this beautiful talk. Do you have any questions?
Tengo una duda respecto al método. Se hace incidir luz y hay un detector enfrente, sobre todo para los pacientes diabéticos. ¿Dónde se coloca el detector?
Es una fibra, ¿verdad? Es bifurcada. Tiene digamos,
What's the method to detect
ahí se conecta.
in the patients?
Y finalmente,
We put the
digamos,
light source
espectrograma,
directly
lo que se está indicando
attached
son
to
como
the
las bandas
skin of the
relacionadas con la
patients.
cantidad de glucosa, ¿verdad?
De glucosa.
Y
In
si
the
son pacientes
spectra,
diabéticos, pues
we
entonces ya
detect
están catalogados clínicamente y
we
bueno,
detect
pues tienen
the
un nivel
presence of
de glucosa más alto.
sugar
¿Han
in
podido
blood.
discriminar, por ejemplo, los que son prediabéticos?
Sí.
Can you discriminate between people with low levels of sugar in blood with those or with high levels of sugar?
El organismo, bueno, pues tarda 5 minutos en identificarlo, ¿verdad? Otro biomarcador que analizamos es
Another biomarker is glycosylated hemoglobin.
Y eso es lo que hacemos, ¿sí?
This biomarker is present in blood for 3 months, and this allows to detect and for 3 months the presence in sugar blood samples between health and unhealth patients.
Another question? I have just one quick question. Are you thinking to do something beyond just the research, like technological transfer? I know in Mexico it's very difficult, but if it's quite new, are you thinking just maybe go beyond Mexico?
With respect to make or our device, we are making our
There are questions online.
Yeah, very quick question. So there are many commercial chips available at market to monitor the glucose, diabetes, everything. So how compatible this technique, Raman spectroscopy, because this technique is expensive and also very big. We need to measure in the laboratory. So how compatible this technique in order to commercialize to make the measurements in real-time applications.
Commercially, it's very expensive, but we are making our own device. We bought many things. For example, the detector, the microprocessors, the light source, and is more cheaper than one commercial.
So you can make the device like smart chip, or is possible?
Yeah, it's possible. It's possible. But in the market here in Mexico, it's not possible to build any of them. But in the market, there are many.
Using the Roman technique.
Yeah.
There's no more time for questions. Thank you very much for attending. Okay, let's continue with our session. The next presentation is from Valentina Bastida. It's a design of a development board based on the microcontroller at Mega T28P, including a symmetric low noise voltage source. Please.
Good evening, everybody. I'm going to be talking about the design of a development board based on the microcontroller at Mega 328P, including a symmetric low noise voltage source. Okay, so I'm going to begin with the motivation of this project. First of all, this board intends to complement the capabilities that a commercial development board can offer. This will be done by offering a tool that has integrated a source for analog signal conditioning, while simultaneously having the capability of making digital processing. This board also looks forward to attending specific necessities of biomedical instrumentation. Therefore, we want it to be low noise, small, and practical. Also, as many instrumentation projects require nowadays digital processing, this board means to offer both parts. This project was also designed intending to give a working tool for formation courses of digital and analogic electronics. And finally, the purpose of this development is to offer a tool that can be used for more complex instrumentation projects that require analogic and or digital conditioning. Next. So I'm going to begin talking about the development stages of this project. We began designing the symmetric source. Afterwards, we did the component choice and the rectification circuit test. This part, specifically, what it does is to give a way to disconnect a capacitor so that we could visualize the process of voltage rectification. Later, we did the integration of the switch to the symmetric source. We designed the circuit for the voltage dividers so we could do the digitalization of the output of the source. Then we chose the potentiometers for regulating the voltage so we could have the best resolution possible. We designed a switch that could enable or disable the analogic digital channels, and we did a code for reading voltage at the output of the source. And finally, we implemented some digital functions. Basically, we modified the bootloader of the microcontroller so we could work at a frequency of 8 megahertz, and we added the reset button for the circuit. So in this image, what we could see is the block diagram of the development board. It is basically divided in two main sections. This one is the analogic is the fixed voltage source. It has the rectification switch and the rectification pins where we can visualize the rectification voltage or the ripple voltage. And we have this block that is for adjusting the voltage of the symmetric source, and an additional switch that is the AD enabler. And for the digital block of this development board, we have the LCD connection pins, the microcontroller with its input-output pins, and a reset button. Well, for the results, what we did is this printed circuit that is basically the real prototype of the block diagram that I just showed you. So we have all these components that are part of this development board. The main ones are the hardware architecture, the microcontroller, the LCD pins for interacting with the microcontroller, the voltage regulating zone, and well, the zone where we can have our output of the symmetric source. So as part of our results, we wanted to guarantee that this development board worked in the best way possible. So on table 1, what we can do, what we can see is the results of several measures that we took to know what the stabilization time of our source was. So what we did was to connect a charge of 150 milliamperes, and we fixed an initial voltage, and we took time of how much it took for the voltage to reach its final value. And well, on table 2, what we can see is the measures that we took for the signal and the noise. This is because, as I have mentioned earlier, one of our main goals is to attend specific necessities of biomedical instrumentation. So we wanted to know how much the noise at the output of the source was. So what we did was a conditioning circuit using the symmetric source, where we had an initial waveform generated that had an amplitude of 500 milliamperes, and it was and a frequency of 250 hertz. And we did an amplification with operational amplifiers, and we measured the noise at the output of the conditioning signal. What we can see here is what the rectification switch does, and this is what we can visualize in the rectification pins. Figure 3 is the full wave voltage rectification that has an amplitude of 19 volts. And on figure 4, we can see the ripple voltage of the rectification. Finally, we did a test for a biomedical application. So what we did was to design a biopotential acquisition circuit. And this was for an electrocardiogram, and the circuit that we designed was basically the block of biopotential acquisition with an instrumentation amplifier that had a gain of 39 decibels. Afterwards, we did a low-pass filter and a high-pass filter with cutoff frequencies of 241 hertz and 1.06 hertz. And finally, we did an non-inverting amplification with a gain of 33 decibels. For the development board parameters, what we have for the analogical block is a voltage source that goes from 1.9 to 19 volts with a maximum of 1.5 amperes, a fixed source of 5 volts, an on-off switch, an enabler and disabler button for the analog digital conversion channels A1 and A0, and an LCD brightness regulator. For the digital block, what we have is the
microcontroller with an operating voltage of 5 volts and an operation speed of 8 megahertz, and 6 AD converter channels and 16 input-output digital channels. Also, we have the reset button. As part of our discussion for this project, we have that the stabilization time that will also be the response time of the development board was an average of 16.26 seconds. And also the final voltage will be 99.67% of the initial voltage, meaning that there is an error associated with this source of 0.33%. Later, we have that the signals conditioned via this symmetric source will have an SNR of 24.68 decibels in average, which for signal conditioning, it is ideal to be above 20 decibels. Also, it is possible to visualize the ripple and the rectified voltage. The ripple voltage will have an amplitude of 100 millivolts maximum, and the rectified voltage of 19 volts. And finally, the development environment of Arduino allows us to work with this development board, but we had to make slight modifications to it so that we could use the microcontroller at the frequency of 8 megahertz. Also, via this development environment, we can do serial communication with the programmer. And as our conclusions, we have that the ATmega328P is the ideal hardware for our project because of its flexibility, cost, and reliability, and also because it is easy to learn for all users. The board allows us for working with analog and digital signals, but it also makes possible understanding the voltage rectification process and visualizing it without any risk for the user. It allows the development of more complex projects in electronics, and it will be useful in applications where space optimization is essential. The symmetric source that we implemented is safe and stable, and the signal-to-noise ratio is good for biomedical instrumentation. Also, it will be a useful tool for electric biopotential, but its reach of this project includes any type of electronics project that functions within the parameters of this board. And finally, we did the proof of concept for a biomedical application with a system of acquisition of the heart biopotential, and we did see that it was not affected by the potential line interference noise. Thank you very much. Finally, I would like to acknowledge all my co-workers that helped me through this project, and that is all.
Thank you. Is there any questions?
Do we have questions online?
Sure. Question? No questions? I have one. Why are you using this microcontroller, the ATmega one? As I know, for example, the microchip microcontrollers, these big, are cheaper, and there are a lot of resources. So why do you use this?
Well, we began developing this project without having in mind any microcontroller, but after having worked with it in various projects, what we did see is that it is a very low-cost architecture, but also it is widely used in many countries and in many levels of academic research. So we thought that it would be a suitable architecture because it is already known, but we wanted to give it a different approach.
Thank you. Is there any other question?
How do you manage to get the input to your electrocardiogram into your board? What was the source? Was it analog?
Yes. Well, it is two different circuits. For the electrocardiogram, what we wanted to do was to use the symmetric source and see that by condition any other circuit, the final signal will not be affected widely. But yes, at the output of the symmetric source, what we did was connect that part to the input of the circuit for the electrocardiogram acquisition.
Any other question? So thank you very much for your presentation. Okay, the next presentation is by Shailendra Singh. It's a performance assessment of N-plus silicon germanium based the electrically modulated vertical tunnel field effect transistors for lower power biomedical application.
Can you share your presentation now?
Not yet.
Okay, you can try now. You have permission. Okay, we can see your presentation now.
These are my outlines. And in the outlines, introduction about the tunnel FET. Those who are not aware with this device, we have been compared this with the previously MOSFET, which has been conventionally running, and we have all studied aware about this MOSFET. Also, what problem we are facing with and how we have been rectified with our proposed model. So its findings, energy band diagrams, result and discussion, conclusion parts, publication regarding proceeding details and references. So with the coming to the introduction, so we all know about this Moore's law, and beyond the Moore's law, which has been a scaling measurement with the evaluation of years to the decades of the number of transistors, which has been continuously increases. So some new technology has been arises, like some new roadmap has been came up. Like ITRS is one of them. ITRS is the International Trade Roadmap for Semiconductor that has been that shows that the physical gate strength of the transistor will shrink up to 2025. So, but ITRS shares, Palilio Gardley said that it can be possible to go vertical just because it will get saturated somehow. So, for this particular thing, if we're going to see the chart, that in this chart, if we look at the channel length of green color, this is a gate length. So this is continually decreasing with the coming number of years, and many more diminishes has been involved with the certain technology. So thus now the ITRS has some factors, and above this we have IRDS. So IIDS said that we have also include the factors like environmental safety, health, and sustainability. So difficulties with the MOSFET we having like if we shrink our device, then leakage current will increase, power supply will be affecting, last short swing terminology will be going to see later, low switching speed, short term effect, power dissipation, low reliability. These are the terms which will be affecting and find difficult in the MOSFET. So coming to the solution of this, these are the latest devices like CNT FET, FinFET, junctionless, nanowire, and tunnel FET, among which we are going to work upon tunnel FET just because of its easiness and all other are complex in nature. So tunnel FET is basically containing consists of all the structure as we have ring of the MOSFET. Simply we are replacing the N type MOSFET, N channel means we are replacing only source time doping of the P plus, and the structure become PIN structure. So rest all the things will be other things will be remain same, but in a scaling dimension. And this work about the technology of the band to band tunneling. What does it means? Means earlier, earlier we are working with the thermionic emission. The charge carriers from the conduction bank will be get transmitted to the source drain side, when this will be get diminished by the drain by applying the VGS gate voltage. In this the charge carriers will tightly get penetrated to the conduction path of the drain side. So with these benefits, we have very steeper slope which has been struck down to 60 millivolt per decade, and we have very large on current, and low off current means the ratio will be increased, will be reduced short channel effects, and ability to do work in a super and sub threshold voltage. So geometry scaling will be is not so much affecting to this, so diminishing parameters can be affecting. So this is for the one
transistors.
in which I'll tell
On
you
the top,
this
you
is the
see
penetrating medium
a
between
current
and this is the
density
suppressing
plot
between
where the red streak
suppressing
is the
between
chart where the
of
current density through the device.
thermionic emission.
Have interference with
This
other
is the slope
presentation.
that is straight into
Of
the
a conduction band and a
per
valence
decade
band,
means it's a parallel to this, and
where the
this is showing
MOSFET is
this is
modulated by a
showing
gate.
how steeper they
And
have
you
been.
see
We had interference with other presentation. To start again, to rewind about
Concentration is
15
also
seconds. Thank you.
calculated.
There is.
Parameters can be affecting. So this is for the one in which I'll tell you this is the penetrating medium in between, and this is the suppressing in between, suppressing between of the thermionic emission. So this is the slope which has been straightened to the 60 millivolt per decade, means it's a parallel to this, and this is showing how steeper they have been cut. So now this is a performance in which these parameters effectively changes, like body thickness, gate oxide, very oxide permittivity of this, and the doping concentration, which will be directly affecting to the energy level. For high doping concentration, they have been more closer to them, and in which these doping concentration is also affecting the ambipolarity system. So with the conventional, we have to these process which has been required making cost effective. So a diffuser, ion plantation, high temperature electrostasis. So this is the verification which has been done with the conventional one, vertical defect, just to validate our model should be in a right direction. So these are the certain credentials which we have taken of this one. And this is the drain characteristics, which consists of a major part of the device, which believes that our device is working will in a direction. So this is a drain current we are getting as off current 17 to the 7, and this is a variation which has been done with the point with the circadian 0.1 to the 0.5. The major part is this we have taken up to 0.64. So very low voltage is required to form of this. And this is a variation which has been done with a different dielectric constant which we are using as a gate oxide, like HFO2 is represented by the green color and the so on. Means increasing from the SiO2 to the HFO2. These all are continuously improving with the increased value of the K. Now, with this energy band diagram, so this is for all these energy band diagram. The more closer has having of the HFO2 rest of away from the distance. So this is the electric field. Again, we can say that for HFO2 this is showing the best one, and for the HFO2 surface potential is come out to be as best one among all other four dielectric constants. So we can once one can straight out conclude that HFO2 can be done. We can find out the different biomolecules equivalent. So coming to the conclusion part, what we actually found in this paper. Okay, so in this paper we basically investigate the electrical characteristics. So in the electrical characteristics, what we have investigated about the it's a silicon germanium mole fraction variation. We have sent about the different dielectric constant value which has been taken apart to the channel from both the sides HFO2 and SiO2. They have been equalized with their 3 nanometer, 0.5 nanometer with the gate side thickness. So we have varied with these, and we have to find out the optimized value of the mole fraction, and we have optimized the value of the material. So HFO2 is the optimized value of the material. 0.9 is the silicon mole fraction which they have found as optimization. The second point is these are also playing roles for the various thickness in the length of the pockets. Like if we're going to change the pocket size of the cavity, so which molecule size will become, and inside to measure the sensitivity. This also we come as a conclusion part. Along with this effect, various gate oxides like HFO2 is found to the highest sensitivity than others. So measurement of the cavity for the positive and negative charge molecules also discuss the to evaluate the characteristics for the different positive and negative biomolecules can be sensed to this. So we can also acknowledge that the device is more influenced for the negative charge biomolecules rather than the positive biomolecules. So these are the few references which I have took, and these references with a good identification channel we have took, and so thank you. I also like to acknowledge Dr. Balvinder Raj, Assistant Professor in IIT Jalandhar, to facilitate his lab materials to us and research environment to carry out this research work. So with this, I hope I thank you all the listeners and all the authorities, those who were patiently listening to me. And I thank you all for giving me a chance to present before you my topic of performance assessment of dielectric DM vertical defect for low power biometric application. So thank you.
Thank you as well.
Thank you for your presentation. Do you have any questions?
No, no está presente. Yeah, how? Yeah, how is present? Yeah, how is present?
Okay, the next presentation is by Jia Hao Ang, a hybrid cluster learning and segmentation approach for the detection of acute lymphoblastic leukemia.
Yeah, so I'm just trying to share my screen, but I can't. Okay.
Now we can hear you.
Okay, thank you.
We can see your presentation now. When you're ready.
Hello and good afternoon to everyone. First of all, I would like to thank the organizers and chair for hosting the event and for the opportunity to speak at the second international conference on trends in electronics and health informatics 2022. My name is Jia Hao, and I am the representative speaker and first author for the paper ID 20 titled A Hybrid Transfer Learning and Segmentation Approach for the Detection of Acute Lymphoblastic Leukemia. The corresponding authors, Nazia Hamid, Adam Walker, and Mahmoudul Hassan, were associated with the University of Nottingham and Angela Ruskin University in Cambridge. First of all, some background about the topic. Leukemia is a fatal type of blood cancer, which normally starts forming from the bone marrow. This can cause abnormal white blood cells, which constantly grow and divide, and therefore, in the end, straying away from its original function. So, according to the National Cancer Institute, leukemia is the 6th most commonly diagnosed form of cancer, and the most commonly diagnosed form of cancer seen in children. Acute lymphoblastic leukemia itself, also known as ALL, contributes towards 74% of all leukemia cases, and is therefore the focus of this research. ALL itself spreads aggressively and requires treatment as soon as diagnosed in order to increase the chances of the patient's survival. And conventionally, ALL is treated manually by a hematologist through bone marrow aspiration and biopsy. But the mild symptoms and nature of this disease, the ALL disease, as well as the manual methods of diagnosis are prone to human errors caused by external factors such as if they're overworked, stressed, or they lack experience. Therefore, we have conducted our research to aid in this problem with the following contributions. We have developed a methodology to detect ALL and to produce a computer-aided diagnostic system as seen in the images on the right-hand side. We have trained a model using deep learning techniques to classify lymphocytes, the purple blobs, achieving an accuracy of 89.7%. We have also developed an accurate object detection and image segmentation pipeline to detect lymphocytes, once again, the purple blobs in the blood smear images, which are potential blast cells, or for simplicity, blast cells are also known as cancer cells. We have also provided open source access to the data of training images and testing images, generally the whole data set that we have produced using coordinates that are provided by expert annotators in the IDB1 dataset. So to fill in research gaps, we have conducted thorough literature review. To summarize our findings, majority of the authors classified full blood smear images, hence our decision to produce work which is able to come up with an object detection methodology to individually detect lymphocytes rather than the full image. Besides that, authors were mostly using support vector machine as the classifier, and so we decided to experiment with the new XGBoost algorithm. Next, some authors did not carry out data augmentation and K-cross validation, which takes into account generalization. Lastly, some authors had only a small set of test images, but because we cropped out individual lymphocytes using annotation coordinates provided in the IDP1 dataset, we had a larger data set to train and test on rather than just using the full blood smear images, which is a smaller data set. So comes the methodology. The overall methodology is presented here in this image, used for our computer-aided diagnostic system. We start off by carrying out our image segmentation pipeline process onto an input image. So an input image is firstly passed through our image segmentation pipeline, right? So then this will segment the individual lymphocytes, once again, the purple blobs within the blood smear images. And then this produces individual prospect blast cells. For the standardization and to reduce bias, we resized and rescaled all the cropped images to 256 times 256 pixels. These are then individually fed as inputs into the exception pre-trained network. The exception network is a pre-trained convolutional neural network, which we utilize here as a feature extractor to carry out transfer learning. This allows us to produce feature vectors, which are then flattened and then finally fed into an XGBoost classifier. This produces a final prediction layer, which will classify the cropped image as either a blast cell or a normal cell, right? Lastly, we draw bounding boxes onto the blood smear images. If the classified lymphocyte is a blast cell and cancerous, we draw a green bounding box onto the image. Otherwise, we draw a red bounding box. This is the overall methodology that we use. And moving on to the next part of our methodology is the data set. For the data set, we have used the IDB1 dataset and utilized the annotated coordinate file, which contains the middle X and Y coordinates of each blast cell within the full blood smear images. So generally, there is a file which contains X and Y coordinates of the center point of each of the cancer cell. To produce our training and testing dataset, here's the algorithm that we used. Firstly, we start off by initializing a margin pixel error or a margin error of about 42 pixels. Then for all the full blood smear images, we carry out a loop. Firstly, we feed the whole image into our segmentation pipeline, which will then segment and crop out all the region of interest. After that, we compare each region of interest to the coordinates within the annotation file, the middle coordinates as mentioned previously. And if it is within the 42 pixel margin, we will add it to the blast cell folder. Otherwise, it goes into a normal cell folder. And in the end, we ended up with 511 crop blast cells as compared to the ground truth of 510. After that, lastly, for the data set, we carried out data augmentation to reduce data scarcity and to increase the sample size. At the same time, we simultaneously ensured that the number of individual class samples are balanced as seen here, from 511 to 710, 530 to 710. This also reduces the overfitting and allows for the training data to consist of a more comprehensive representation of raw data features that may be seen in maybe future testing sets. Lastly, for our methodology breakdown is the segmentation pipeline that I've been mentioning. For object detection, image segmentation definitely plays a crucial role. So we have therefore built an accurate image segmentation pipeline using state-of-the-art traditional image processing techniques as seen in the diagram. Firstly, mainstream filtering is carried out to soften the image. This is then followed by converting RGB to CIE lab color space. This allows us to carry out single channel extraction and only utilizing the B channel. We then use also thresholding, followed by EDT watershedding, which separates the individual parts of the segmented items within the whole image, allowing us to crop out the regions of interest. Lastly, comes to the results. We have used a K-fold cross-validation value of 5, hence carrying out 5 cross-validation during the training and evaluation process, thus reducing overfitting. For training and testing, we have used a 80:20 ratio, which ends up in 284 test images and 1,136 training images. When conducting experiments, we have tried with various pre-trained networks, and we have found that exception outperforms other networks in accuracy, while also outperforming in other evaluation metrics. At the end, it comes down to 89.7% as the highest accuracy. For the runtime analysis of segmenting and classifying blood smear images, it is highly dependent on the density of lymphocytes within the blood smear samples. However, it generally takes less than a minute for full segmentation and classification. Here are some of the examples of the final produced results. The small X within the lymphocytes are the ground truths, and the green bounding box, as mentioned earlier, are the indication of cancer cells, and the red bounding box are normal cells. So in conclusion, we have achieved our research targets and we're able to produce an accurate computer-aided diagnostic system methodology to detect and classify acute lymphoblastic leukemia. We have also managed to produce a new open source dataset created from the Origin IDP1 dataset, which future researchers can use. Lastly, we have filled in research gap left by previous authors by addressing problems such as overfitting and bias caused by model variants, generally providing an unbiased evaluation of performance through fair trials and experimentations. But due to time constraints, we were unable to carry out further research to conduct dimensionality reduction and feature selection, which potentially reduces computational runtime and resource consumptions. This will therefore be prospect and labeled as future work. Lastly, once again, Thank you very much, and thanks for taking your time to listen to this talk, and we hope that you have enjoyed it.
For the author of the work, how kind of leukemia can you recognize?
For now, the data set is only aimed towards acute lymphoblastic leukemia. There are the other 3 kinds, myeloid as well. But because we trained the model on ALL only, as of now, I would say towards only this one type.
Can you repeat the last? What kind is leukemia you can recognize?
Acute lymphoblastic leukemia, specifically this kind. We have not trained the model on the other types. So as of now, just acute lymphoblastic leukemia.
Okay, thank you.
Thank you. Yeah.
Another question from the audience? No, it seems that there are no more questions. Thank you for your participation. Yeah, how?
Thank you. Thank you.
We are going to take a 15 minutes break, a coffee break, and we will be back.
¿Ahí estás, Yair? Yair,
Sí, aquí estoy, doctora.
a ver, déjame, ¿cómo se llama? Conectar esto.
Ah, sí, ya escuché el ruido.
¿Ya
Bueno,
oíste el ruidito?
sí, ahorita ya lo escuché.
Ese.
Pero bueno, cuando presenta no se escucha.
Ajá, capaz
O sea,
ese es el de la bocina.
pero cuando pone el video, no, bueno, al menos aquí no se escucha.
No puede ser el cable, pero es que auxiliar sí no tengo.
Ahí está el ruidito.
Hacer el cable.
Oye, Yair, voy a
Sí.
compartir la presentación, pero la voy a compartir nada más con el, ¿cómo se llama? Sin bocina.
Ah, ok. Bueno, pues a ver si se escucha. Lo que puede hacer es poner el micrófono lo más cerca de...
Es que era una bocina externa.
Ah, ok, bueno.
Déjame ver si la puedo, déjame compartirla.
Ajá.
Y ¿dónde está el ratón? Y ¿cómo se llama? Y ahorita vemos, ¿no?
Sí.
Espérame tantito.
Ok.
A ver, ¿dónde está el coso
No sé.
No sé. A ver, voy. Dice Disgule. Sí, gracias.
Me dice si le funcionó o no.
Sí, gracias.
Puede mirar.
Sí. A ver. Y me dice si se oye. Si le subo todo el volumen de la lab. Apárate. Ya. Espérame un tantito. Creo que ni se oye, ¿va?
No, no se oye nada.
Audio.
Ahí se escuchó algo.
Sí. ¿Ese es él, no yo?
The title of my presentation is Logistic Regression Approach,
Ahí se escucha.
Joint
¿Pero se oye
Classification
bien?
and Feature Selection in Lung Cancer.
Ahorita le digo, permítame.
Data. Lung cancer
Voy a
screen
ponerlo acá en la bocina.
identify patients who are at the most risk of lung cancer. Here, a very brief introduction to lung cancer screening. Lung cancer screening is an intervention tool for early detection of lung cancers.
Un poco bajito, pero se oye.
Sí. Es que no sé qué trae la bocina ahora.
In literature shows that lung cancer screening is a very effective intervention tool. Early detection
Sí,
of
se
lung
oye.
cancer is very important because lung cancer is one of the deadliest cancer in the world.
Sí, sí se oye.
Diagnosed with late stage lung cancer had a
Y ahora tú, ¿qué traes? Que no se oye, ¿verdad?
No, ahí no. Pero así como lo habían puesto, sí se escucha.
Electronic health records. Clinical Practice Research Data Link, CPRD, is an EHR database that collects patient data from many general practitioners rather than from screening trials.
¿Ahí se oye?
CPRD data has been used
Sí, sí se escucha.
of patient
Entonces no le voy a mover nada y así que se quede. Si no voy a tener que pasarlo al otro, ¿no?
Ujú.
Ok, bueno, entonces esa va a ser la que se va a presentar. ¿Vale? La dejo, ya la dejo proyectando.
Ok, estaba preguntando el doctor Enrico, vamos a pasar el trabajo 25, ya después el suyo, el 30.
Perfecto, gracias.
Sí,
A ver, espérenme, ¿quién cuál va? Ah, sí, va el 25 y después el del doctor Enrico. Ajá.
está en línea igual por si hay
Ah,
preguntas
ok.
del público.
Sí, ok. Sí, nada más que tenemos este problema con el audio.
Se pueden pasar el vídeo, es mejor. Envié el vídeo, sería mejor pasar el vídeo, más si no, puedo hacer la presentación en vivo.
Tenemos el video, doctor.
Ótimo, entonces utilizamos el video.
Ok, está bien. Bien, entonces la dejamos ahí puesta, ¿no?
Voy rápido por un café y regreso. Pero ya está la presentación.
Sí.
We are back. If you want to put your presentation, you can start.
Hello.
Ready?
Third screening
1 second.
using CPRD data.
Now we are ready.
Yeah.
The title of my presentation is Logistic Regression Approach to Adjoint Classification and Feature Selection in Lung Cancer Screening using CPRD data. Lung cancer screening aims to identify patients who are at the most risk of lung cancer. Here, a very brief introduction to lung cancer screening. Lung cancer screening is an intervention tool for early detection of lung cancers. Evidence in literature shows that lung cancer screening is a very effective intervention tool. Early detection of lung cancer is very important because lung cancer is one of the deadliest cancers in the world. Patients diagnosed with late-stage lung cancer had a 1-year survival rate of just 15%. Lung cancer screening still meets difficult challenges. 2 examples. 1, lack of the patient symptom awareness, and the second, the underserved high-risk population. To deal with such difficulties, one possible solution is increase the use of electronic health records. Clinical Practice Research Data Link, CPRD, is an EHR database that collects patient data from many general practitioners rather than from screening trials. CPRD data has been used to generate a cohort of patients for retrospective clinical studies. This cohort can be used to select a subpopulation of patients who are at the most risk. AI techniques and machine learning methods plays important role in this task. Here are very brief description of the data we used. We used 10 CPRD data. They are lung cancer COPD, a group of lung conditions which cause breathing difficulties. Personal history of lung cancer, family history of lung cancer, BMI, body mass index, status of smoking, never smoke versus current smoke, the starting date of smoking, the stopping date of smoking, the number of cigarettes per day, the number of cigars per day. Here we define 2 new feature variables. Smoking duration is the difference between the stopping date and the starting date of smoking. The smoking intensity is the weighted sum of the number of cigarette and cigar per day. This gives us in total 8 variables. Lung cancer is the variable we are going to use to predict, and the remaining variables are feature variables we are going to use for making prediction. Here, a very brief introduction to the model we use. We use the logistic regression. The formula below describes the logistic regression. Y stands cast label. X stands the feature vector, W stands weight vectors. Weight vector W is the corresponding weight of X. The logistic regression model we used is constrained by L2 regularization. In our work, we have about 500,000 controls and about 5,000 lung cancer cases. Therefore, we have a class imbalance. Therefore, we adopt a number classification by undersampling of majority class and majority voting. Feature selection is based on the absolute value of the weights. The higher absolute value of weights, the more important is the corresponding feature. Here are summary of our classification results. On the left, we show our hyperparameter training results. An x-axis is hyperparameter, which is regularization coefficient, logarithm. Y-axis is estimated accuracy. We see the optimal hyperparameter is about 0.5. In the middle, we show the estimated testing accuracy in a box plot. We can read from the box plot that the median testing accuracy is about 0.75, and 50% of the estimated accuracy are between 0.73 and 0.75. On the right, we show a confusion table. We can read from confusion table that our sensitivity is about 84%, and our specificity is about 64%. We compare our results with the results of a similar study in the literature. The slight difference between these two studies are we have different data source. We use CPRD data. The reference study uses data from screening trials. Second, we have slight difference in cohort size. More importantly, we will have a data set with class imbalance. In the reference study, have well-balanced data set. In terms of classification results, our sensitivity is about 84%. For the reference study, one data set shows 83%, another data set shows 71%. For specificity, our specificity is 64%, and the reference study has specificity 63% in both cases. In summary, both studies have a similar results. Finally, we present the feature selection results. For each of the individual features, we plot its histograms. X-axis is the absolute weight values. Y-axis is the histogram values. And here we can see for COPD and smoking status, its value is about not 1.4, which are higher than other features. And for smoking duration, it is about 0.4, but it's clearly away from 0. For the remaining three features, their value is close to 0, about close to below the 0.2. In summary, COPD and smoking status are two most important features for the classification task and for the screening task. Conclusion, first, given the logistic regression is a predictive model, the predictive performance is a comparison between our study and the reference study. Second, a sample supervised feature selection algorithm can predict the most important features available, which is in line with the expectation. Third, limitation. More CPI data should be included for study. The feature variables engineered can be further improved. Many thanks for your attention.
Okay, we can start with the presentation of Erico Acevedo.
Hi, everybody. My name is Erico Azevedo. I'm PhD in clinical psychology and also in electrical engineering. It's a pleasure to be here with you, sharing the results of this research about the information field experimental test in the human realm. First of all, I'd like to thank on behalf of all technical sponsors and organizers, Aniban, and also Professor Eduardo Lugo for all their support in taking part in this incredible Congress. As I said, this Congress is about, this research is about the information field classical theories and experimental tests with human beings. Every research question has a history made of great human beings. It's not different in this case. So we could move back to Gurevich in Russia, studying onion root cells and their emanation of electromagnetic waves, to modern times with researchers like Luc Montagnier, Farhadi, Hameroff, Bandiopatii, and so many others that are showing us that there are quantum level phenomena happening also in living beings. The basic question is, can human beings, and more generally speaking, all living things communicate at a distance beyond 5 senses and electromagnetic schemes and chemical also schemes? Speaking with Charles Darwin, communication is considered to be a result of our evolutionary process. Many researchers like Sheldrake who have made a deep dive on this kind of phenomenon, distant communication phenomenon. Of course, they should be supported by evolutionary process, but it's presupposed in the end the existence of some kind of information field. He called morphic field. Other studies about intuition show also that this long distance capacity of perceiving phenomena in reality must be connected with some kind of evolutionary process. For Meneghetti, who came from a more clinical and psychological approach, he observed this phenomenon while people were telling him his or their dreams. And then he called this phenomenon semantic field, an information transducer without energy displacement. He used it in very practical ways and forms, but of course, the task of describing it in a physical terms should be a task of engineers and physicists. Well, the first insight to conduct this research came from a previous research in clinical psychology, where we measured signals from 162 psychotherapy sessions using oximetry, pulse rate, SpO2, and GDV Killian digital cameras. Signals were measured and compared between subjects and psychologists, and their correlations in their behavior were really amazing. Precisely at the moment where the patient was telling his dream. Correlations and signals didn't behave so precisely when the situation was telling the problem or telling the drama or in a regular conversation. But when it comes to telling the dream, this Spearman correlations come up to 95-96%. Was it a mere coincidence? Phenomenon of this verbal communication or non-verbal communication, but physical, understood in terms of body language? Could it be tested with the distance and barriers, eliminating all kinds of communications between these two subjects? Then we got inspiration from Alan Aspect's work, and the proof of existence of the entanglement phenomenon. Basically, 3 elements of his work were very important for us: used by analogy, eliminating hidden variables, the randomness in relation to the moment of interference, and of course, here, what information would we choose to represent the energetic state that would lead from one place to the other? So here we have chosen dreams based on their efficiency in producing changes in the ANS balance. Experimental design included then a considerable distance, 250 meters, no mechanical, electromagnetic waves allowed, of course, no communication between these two guys. One of them would write down on a piece of paper the dream and would go inside the Faraday cage. The other guy, in a random time, in 20 minutes of experiment, would open this piece of paper and silently read its content. In the control group, the content would be changed by a computer manual. Here we see the configuration of the labs. There are different buildings, different blocks, Faraday cage, etc. The instruments I have already mentioned, so pulse rate, SpO2 measurements, and also RR intervals with posterior heart rate variability analysis, and the energy in joules measured with the GDV digital camera instrument. Data was normalized considering 3 moments. So if the reading of the dream or reading of the manual would have a typical duration of 1 minute, then we would have 1 minute called before, 1 minute called reading, experimental or control groups, and 1 minute called after. And then all these signals were normalized in terms of z-scores, coefficients of variations, and so on. Few questions guided our analysis, but basically we're looking if subjects inside the Faraday cage differ during the moment of reading compared to experimental versus control groups. Of course, that we would expect that outside, those who would read the dream would have their NS balance affected, but it wouldn't be expected that subjects inside the Faraday cage would have also this behavior. Results were really very unquestionable in terms of all variables confirming, be it pulse rate and SpO2 variables, GDV variables. Every instrument confirmed these important changes precisely at the moment where the dream started to be read outside the Faraday cage, and subjects inside the Faraday cage would change. When comparing with control groups, where basically nothing would happen inside the Faraday cage, some small changes outside for those who were reading, which was also expected. Also with variables related to heart rate variability, which confirmed also these important changes, very strong changes, sometimes 17 times more in terms of change for those in experimental group, like in low frequency, high frequency, total power, and so on. And also SNS and PNS results in a global manner. Another tests were also conducted, and they all confirmed also the same results, or basically all variables except SpO2. And this would be very relevant P numbers. In terms of discussions, we went through in the article what would be the physical explanation, could be the physical explanation for this. So we took support in David Bohm's de Broglie pilot waves theory, and we reconciled those first situations in the quantum level, subatomic level, with the integration function of the nervous system until the formation of images that come to our, sometimes they come to our consciousness, sometimes they don't come, but anyway, they change our ANS balance, generating emotions and vibrations. Conclusions and future work. Here, basically, we confirm that human dreams deeply affect the ANS balance of subjects both outside and also inside with barriers, which was a real breakthrough, number 2. And very importantly, the use of dreams affect that process all cultures, ethnies, historical periods of humanity. It's just a human phenomenon. But it's a natural bridge between scientists from many areas and epistemological approaches, maybe creating also a new standard in how to establish results, consistent results, and repeatable results in this kind of research. Thank you very much. I will open for questions. I'll stop sharing my slides. It'll be a pleasure to meet you.
We have questions online. The next talk is ready.
Yes. 1 minute.
When you're ready.
Presentation consists of the basic idea of this particular core architecture, followed by introduction to the beyond 5G and 6G based application area, which will be followed by history and an ongoing trends of mobile subscriber with various generating routing core module for beyond 5G based wireless camera sensor network. And then that will be followed and ended up by the present application area with B5G based on wireless camera sensor network, and then conclusion followed by references. Now the basic idea for making this core architecture for beyond 5G wireless camera sensor network was on the theme of cooperative communication. Now the cooperative communication in the wireless communication networks is basically concerned mostly with the wireless network of the cellular or ad hoc variety, where the wireless agent, which we call users, may increase their effective quality of service via cooperation. And what do you mean by cooperation? The cooperation leads to interesting trade-off in the code rates and transmit power, energy consumptions, load balancing, life of the network, and many more aspects related to the quality of the service. Now, based on that, we have the systems such as telecom or cellular, in which the users communicate with the central base station, which either can be main switching center or base switching centers, which offers possibility of centralized mechanism. Then the basic idea also incorporate that the systems like wireless sensor network or wireless camera sensor network typically do not have any centralized control, but are distributed cooperative protocol, in which users are able to independently decide with whom they want to cooperate or whether they do not want to cooperate, in terms of offering any kind of frequency spectrum just to use when they are idle for a brief period of time, or for any given instant of time. Then we can also have this introduction of wireless sensor network before we go for the core architecture of this beyond 5G network. So wireless sensor network or wireless camera sensor network are typically constituted of tiny electromechanical devices, which are sensor nodes. Sensor nodes communicate via radio frequency signal, which one or more powerful sinks which are called as base stations. There are two types of modes in the sensor nodes link communication. One is set to with a single hop communication, one is set to with a multi-hop communication. Sensor nodes are also classified as proactive networks and reactive networks on the basis of their functionalities. Normally, proactive networks are not being used on a regular basis, because as they are outdated because of their extremely power consuming behavior and low network providability in terms of life, while the reactive networks are more suitable for time critical applications. For the better work and better networking environment, we need to prolong the life of the sensor network, and also at the same time we need to be very efficient if the sensor nodes can work together. Now there are certain silent features of 5G, beyond 5G, and of course nowadays we can call the sixth generation. The fifth generation mobile network, or simply 5G, is a forthcoming revolution of the mobile technology. The feature and its usability are much beyond the exceptions of a normal human being. With its ultra high speed and its potential enough to change the meaning of cell phone usability. So we can see here in this particular diagram that there are a number of features which are actually associated with the 5G technologies, like virtually there is zero latency, speed is up to 10 gigabytes per second, wide range of application areas, ubiquitous connectivity is there. You can find IoT based application areas, software upgradations are there, very high and flexible capacity, faster response time. Then we have cloud computing based application area, resilient computing capability, 100 times more devices can be connected to each other or with each other by this 5G based communication. So these are certain salient features of the 5G or beyond 5G or 6G based cellular or any wireless network. So what are these 5G and beyond 5G technologies in general? I'll be saying these are actually having those particular features like high increased peak bit rate, larger data volume per unit area, high capacity to allow more device connectivity, as I've said in the previous slide also, lower battery consumptions, better connectivity irrespective of the geographical region in which you are actually living in, larger number of supporting devices, lower cost of the infrastructural development, higher reliability of the communication. So all whatever kind of modern day needs are there present in the market or required for any user are actually present in these kind of setup or these 5G, beyond 5G or 6G based wireless networking domain. Now moving on to the core network area that we are actually proposing in this is based upon this architecture of 5G and beyond 5G, which is already there in the market, which have a streaming server, data server, server of the real-time communication control system, policy server. Okay, so these are already available with respect to GPRS, 3G, wireless LAN, and line terminal equipment. So based on, we have made this kit. So this routing core module for beyond 5G based wireless camera sensor network has these kinds of prominent features. Other than these, we are having very low overall delay. Energy efficiency is very high. Rollout expenditure, what we are proposing with this model is very good. Difficulty of the machine-oriented system will be on its side. Future requirement and the number of subscriber that will be supported by any other beyond 5G based communication through this particular model will be very fruitful. In this model, the routing transmitter and receiver can utilize the available spectrum on the cooperative basis, making the optimum use of the available bandwidth. This setup will surely help to reduce the increased bandwidth requirement. And there will be one control monitoring system which would be centralized in nature, just in case if the distributed is available, there will be also a centralized backup power or backup center that will actually be monitoring all over the core module. And multiple access should be given to multi-carrier and data transmission efficiency that will evaluate the user using multi-carrier collision sense, multiple access collision detection. And there will be an encryption modeling also in this particular model that will be used as a selection module while selecting appropriate frequency from the available bandwidth available spectrum. So this particular module that we are proposing here is actually having these much number of what we can say features and that will be available. And we are hoping that this routing protocol, when this will be functional in lab, surely this will help us to have a better cooperative communication, of course, with the integration of 5G or beyond 5G based frequency. As I said, this is what the networking layer versus applications. This is Nishant Tripathi, paper ID is 17. Thank you so much, and I hope the conference does very well. All the best to all fellow participants over there. Thank you.
Thank you very much. Thanks to all the participants. The Congress has concluded.
I'm going to share the next sede for the Congress.
Ok. La doctora Claudia tiene algo que decir. Sí, no, digo, me está diciendo por... Ok. I will give you the microphone. Go ahead. All the audience is now going out.
Dear co-host, I am MD Kaimul Chaman. My paper ID is 36. May I have one, please? Dear host of TEHI 2022, I am MD Kaimul Chaman, and I have already dropped my video recording presentation for paper ID 36. May I have the access for presentation, or will you please play my recorded presentation?
Yes. Dale acceso, Jair, por favor.
Okay, give me a minute. are you able to share your screen?
Yes, I am able to share my screen. So thank you.
Okay, we are able to hear you and we can see now your presentation. You can start.
Is my presentation audible?
Yes, we can hear and we can see you.
I'm playing my recorded video. So is it audible to all the listeners?
Okay, it's okay.
You don't have sound.
You have your microphone closed. We cannot hear the presentation.
Yeah, I have my microphone. Okay, please just a few seconds.
Okay.
So thank you very much. The video recorder has the audio problem. So I'm restarting my presentation. Welcome to the second international conference on trends in electronics and health informatics. I am presenting for the paper ID 36, the paper titled as a smart automation system for controlling environmental parameters of poultry farm to increase poultry production. I am MD Kaimujjaman from Bangladesh, Department of Electronics and Communication Engineering, Haji Muhammad Danesh Science and Technology University. Poultry contributes greatly to poverty reduction and improved food security in developing nations such as Bangladesh as a source of high quality protein. In poultry farming, chickens are highly influenced by high ambient temperatures and relative humidity, and this causes the heat stress related issues in poultry farming that affects the production reduced efficiency and also raises the chicken death rate. It reduces the growth rates, egg quality, meat quality, egg output, and all of which can lower the commercial value, resulting in economic losses for poultry owners. Therefore, in the 21st century, conventional poultry farming faces new challenges, and thus incorporation of modern technology in poultry farming is highly required. The authors of this research are motivated to implement a new smart intelligent automated system in poultry farming that results in better poultry farming to increase the poultry production. So the objectives of the research is to develop a microcontroller-based embedded automation system that provides a suitable environment to poultry house. The system can periodically monitor the environment temperature and humidity levels. Then we investigate the system performance to that of more traditional methods or conventional methods of poultry rearing. And finally, we compare the system mortality rate, live weight gain, feed efficiency, and the possibility of the boiler farms with the conventional poultry farming systems. So as per the block diagram of our developed system, the picture is depicted here. Our system has functioning mainly three works. These are the sensing and rendering, processing and storing, and the third is controlling. So the heart of the system is Arduino Mega development board, which is interfaced with the digital temperature and humidity sensor, time and date module, data storage unit, display unit, and relay switches. The relay switches controls the heaters, coolers, and exhaust fans that are located in the poultry shed with the help of relay switches. So the digital temperature and humidity sensor senses the environment, temperature and humidity levels, and it transfers to the Mega development board. The Mega development board processes and stores the sensor values, and it checks with the threshold values of the system and stores them in the data storage unit. And also, the temperature and humidity levels are displayed through the liquid crystal display. And finally, according to the threshold values of our design system, it controls the heaters and coolers with the help of relay switches. So during the implementation of our system, we have used the OWSP one-wire single protocol, SPI serial programming interface protocol, and inter-integrated circuit protocol. Next, we're selecting the threshold values for the environmental parameters. So during the age of the chickens between 0 to 6 days, we have selected the temperature between 30 to 33 degrees Celsius and the humidity levels 50 to 60%. Similarly, the age for 7 to 14 days, the temperature levels is decreased by 2 degrees Celsius and it's selected at 28 degrees Celsius to 31 degrees Celsius. Similarly, in third week and also the age greater than 21 days, the temperature is selected between 25 to 28 degrees Celsius. Finally, after successfully downloading the data from the SD card, we have analyzed the temperature and humidity level graphs, and we have observed that the temperature in smart system is lies between 30 to 33 degrees Celsius, whereas the environment temperature lies between 29 degrees to 34 degrees Celsius in the first week. Similarly, in the second week, as per our threshold values, the temperature lies between 28 to 31 degrees Celsius, and the environment temperature is between 26 to 33 degrees Celsius. And in the third week, we have observed that the temperature and humidity levels, the temperature is between 26 to 29 degrees Celsius in smart automation system of our design system, but the environment temperature is between 30 to 34 degrees Celsius. So this increased heat causes the heat stress issue and suffocation related issues for the poultry, and that's why the poultry take less feed and their growth efficiency is lower, and also their weight gain is lower. And also for the suffocation and heat related issues, they increases the chicken death rate. And in relative humidity levels, we have observed that the system temperature humidity levels is fluctuates between 80 to 90%, which is much more higher than expected. That's because the increased amount of fecal matters in the poultry house. So then we investigate the mortality rate. So the left figure indicates the mortality rate of the smart automation system. The mortality rate is only 6.7%, and in conventional poultry farming, the mortality rate we calculate is 16.7%, which is much more higher in conventional poultry farming system. Then the feed efficiency, we have calculated the feed efficiency is the net amount of feed used to produce 1 kg of boiler. here we use 5 different types of feeds, that is Nourish, Sun, A1, Aman, and ACI. In each of these feeds, we have observed that in smart system, it requires less feed than the conventional system poultry farming. So poultry owners who are using the smart system can save their money by buying the poultry feeds. Finally, we observed the boiler performance efficiency factor. The factor value should be at least 100. The higher the value, it means the better performance of the boiler. The lower the value, it indicates the poor performance. However, in conventional poultry farming systems, we have observed that some poultry sheds have achieved the value lower than 100, that indicates the poor performance of conventional poultry farming system. But in smart automation system, all of the poultry sheds have gained the value above 100. The maximum value have achieved in smart automation system is 162.5%. So we calculate the farm economy index considering all the weight gain, livability, the feed efficiency, and calculate the smart system economy index and also the conventional system economy index, and we obtain the smart system economy index is 3.89, whereas the conventional system economy index in 2.52, which is very much lower than our designed automation system. So we can conclude that our design performs more effectively to increase the poultry production. So as per our objectives, we have implemented our smart automation embedded system to small and medium scale poultry farms. The system continuously monitored and records the temperature and humidity level. The system performance has been measured and compared with the conventional system. And finally, the mortality rate, feed efficiency, performance efficiency factor, and farm economy index all are compared to the conventional poultry farming systems and obtained better results. So that concludes my presentation. Thank you. Any question?
The presenter is online, so if you have questions, is the moment.
I have a question.
Thank you for your presentation. My question is, why did you choose those humidity and temperature ranges to work?
Because the temperature and humidity levels in the all over the year, that is in summer and winter season. In summer season, when the heat temperature is greater than 33 degrees Celsius, then it might it raises the death rate of the chicken. So this conversely falls the chicken growth rates and also the losses, economic losses for the poultry owners. And for the humidity levels, it creates a suffocation for the poultry to take feed. And if the poultry chickens take less feed, then the weight gain is lost. Then the weight gain is lower than the expected. So it will affect the weight gain and the economic losses for the poultry owners. So that's why I selected the environmental parameters, temperature and humidity levels for the automation in poultry farming.
Okay, thank you very much.
Thank you.
Okay, let's thank the presenter, please.
¿A la doctora Marta o Motfit? No está. ¿Es la doctora Claudia? Ah, ok. ¿Puede prender su cámara, doctora? Ok. La podemos ver. Ok. We can see you. Los podemos ver.
Hello, can you hear me?
Yes, we can hear you, but we cannot see you.
Cannot see me yet.
Yes, I can see you, Mufti. Hello.
Okay, hi Claudia, how are you doing?
Everything is fine. Thank you.
Good. So we have the closing ceremonies
1 second, please.
slides ready here, but there is something which is going on in the YouTube channel. Is it the same one or some other presentation is going there?
It's the
The
same.
presentations are finished.
It's the same presentation. Just is just a little rotated.
Yeah, because I see that there is actually a presentation going on in the same link, or is it a different link? I don't know.
We can see you now.
Anyway, so Claudia, do you want me to share the screen, share the slides, or do you want me to send these slides to you and you can share it at your end?
You can share it.
Okay. So let me just share the screen.
Okay, we can see your presentation.
Okay, so thank you everyone for staying with us in this TEHI 2022 conference, which had been running since the 7th till today, the 9th of December 2022. And we are almost at the end of the conference. So here is a closing ceremony, and I would like to welcome you all to the closing ceremony. So in this closing ceremony, we have programs to have 4 different things. So the first one would be the summary of the TEHI 2022 conference. That will, what was the situation, what did we do, and how many submissions we received. And this is something which would be done by Dr. Eduardo Logo. And then there'll be the best paper awards done by Dr. Severino Munoz. And then the next TEHI 2023 announcement will be done by myself, and the vote of thanks will be done by Dr. Claudia Mendoza Barrera. So with this, I would like to invite Dr. Eduardo Lugo to kindly start with the summary of TEHI 2022.
You have a slide, right? Yes. So thank you very much for these 3 very intensive days. We have 4 keynotes, 4 invited talks, 2 workshops, 38 papers presented. The submission actually was over 100 papers. It was very intense. You see, we had some technical issues. It's not easy to have 1 audience. Here we have 2, and it was international, and it was close to Christmas, as I mentioned before. So for that, I'm very happy of the result. I hope you enjoy it. I found all the talks very fantastic. The level of the talks amazing, and hopefully we'll see you next year in India. Okay. That's all the Mufti. I already mentioned, well, as I said, the 38 accepted papers, we have a ratio of 58% of acceptance in the conference. Next. Okay, so for the proceedings, that's the timeline, 4 to 5 months. they're going to be published. No notifications as I did before. It's going to be me who's going to notify you of the proceedings. Next.
So now I would like to request Dr. Severino Munoz to announce the best papers. So here we have 4 tracks, as we all are aware, that we have 4 tracks, and all these 4 tracks will have 1 best paper award. So altogether there are 4 best paper awards, and these best paper awards were selected from the highest review score that the paper received in each of the category, each of the tracks. So the first track is artificial intelligence and soft computing.
That's you, Mom.
The award for the track 1 is artificial intelligence and soft computing. The paper ID 12, the title, New Benchmarking on Offline Handwritten Character Recognition for Tamil Character Databases. From the authors, Kavita B.R., Noushat, Shafi, Mufti Mahmoud, Faisal Hajamoiddin, and Priyalakshmi Narayanan. Okay, this. Congratulations. Okay. The second paper is track 2, healthcare informatics. Is the paper ID 23. How does microtubular network assist in determining the location of daughter nucleus, electromagnetic resonance as key to 3D geometric engineering? From the authors, Pushpendra Singh, Komal Saxena, Paramadei, Pratik Saho, Kanal Ray, and Anirban Padhyay. Okay, the third paper is from the track 3, IoT and data analytics. The paper ID 1, trimmed TDL-based time to digital converter for time of flight applications implemented on Cyclone 5 FPGA. The authors were Moisés Arredondo Velázquez, Lucio Rebolledo Herrera, Javier Hernández López, and Eduardo Moreno Barbosa. Congratulations. And the fourth one is for the track number 4, electronics, the paper ID 14, title, Performance Assessment of N+ Silicon Germanium-based dielectrically modulated vertical tunnel field effect transistors for lower power biomedical application. From the authors, Sailendra Singh, Ankit Jain, and Balwinder Raj. Congratulations.
Okay, so this is something which now concludes the best paper awards. Thank you very much and congratulations to all the authors for their excellent work being presented at TEHI 2022. Now, well, the announcement of the next TEHI conference. So this is done by myself. So we are very happy that the next TEHI conference will be organized on the 7th and 9th, not December, but in September next year, 2023. And it will be hosted by the Kalinga Institute of Industrial Technology, which is at Bhubaneswar, Odisha, India. So I would like to invite all of you to make an effort. Yeah, well, I know that it's not easy to make this trip, which is quite long, but please do plan it, make an effort to attend the conference there. It's a very nice place. It's a very nice modern institute which has been set only 25 years ago, but well, it has already made the list of 600 to 800 universities worldwide in the Times Higher Education ranking. So it's a university which is growing very, very fast, and they are very positive looking. It will be a very good experience in my opinion. So I would like to invite on behalf of the steering committee of TEHI 2023, all of you to Bhubaneswar, Odisha, India for the third International Conference on Trends in Electronics and Health Informatics, which will be held from 7 to 9 September 2023. With this now, I would like to request Dr. Claudia Mendoza Barrera for the vote of thanks.
Well, in the name of the sponsors, in particular from the College of Physical and Mathematics, we appreciate your participation in this TEHI 2022. And we hope you enjoy it as we enjoy when we develop all the program, and we thanks also to the students that help us all these days. And well, we see you next year. Hopefully we'll be there in India in presence. Thank you very much.
Thank you very much. So see you all in Bhubaneswar, India next year. So this marks the close of the conference. Thank you again.
We couldn't do anything. No, please.
Thank you very much.
Thank you, Darío.
Okay, bye-bye, everyone.
Bye.
Thank you. Gracias. La foto, ¿no? ¿Allá afuera? Sí.
Vénganse para la foto. Okay, this concludes the Congress. Thank you very much.